Hello everybody, another edition of the numeric blueprint. Now today we're going to be talking about the box plots. We're going to be spending some time to look at how we could analyze data with the box plot, and of course to refresh our memory on how a box plot actually works. So I'll try to make this really short, but at the same time you should really get the most out of this video regarding the box plots. Now, I'm just going to quickly show you a bunch of raw set of data. Now, again, usually with data, if we do not find any analysis of any data given to us, it is difficult to make any conclusion from the data given to us. Alright, so given a raw set of data of 15 children, we do really want to spend some time to analyze the data. We have obviously been exposed to things like the mean, mode, and median. Those are very good statistical analysis, or should I say something very fundamental. But today we're just going to go a bit deeper. We're going to dive deeper using the box plots. Now, so having these weights of 15 children, it is easy to identify if we arrange the data from the smallest to the largest, which I believe your teacher would have taught you in schools. Okay, but what I'll basically show you is usually when we do analysis, we try to find some of the most common values or some of the most common measures. In this case, we'll be looking at things like the minimum weight in this context, with the maximum weight, the range, the mode, the median, and the mean. So the range, obviously we do know that that's the maximum subtract the minimum value of the data. The mode is the data that appears the most. Okay, and from the raw data you can see that 35 kilograms obviously appears the most. We have 2 children who has the weight of 35, so that's the mode. And median is basically the data which falls in the middle. Okay, which is 41 kilogram. So basically this is the median. Due to the fact that we have 15 children, so if you think about this, if you have 15 children, the middle position would just simply by taking 15 plus 1 divided by 2, and that should give me the 8th position. So that's why if you count 8 from the left or from the right, so which is 1, 2, 3, 4, 5, 6, 7, 8, that's the median. And of course the mean is basically just adding up the data, and you subtract that by the quantity of the data, in this case which is going to be 15. Alright, but today we're not going to spend too much time on finding the mean, but of course if you do want me to make a video about the mean weight or anything got to do with the mean, please let me know and I'll be happy to make one. So the mean in this case was just 40.9 kilograms. Now if we try to put everything on something what we call a box plot, right, I think this is something that is not really unfamiliar to you. You probably would have seen this before, but just a quick refresher. It's called the box plot. Sometimes we call this the box and whisker diagram. It's because obviously we have the box right in the middle, and of course this is basically the whisker. Okay, and we do know that at this point we're looking at what we call the minimum, at this point is what we call the maximum. Okay, and the box that has like 3 different lines here, this basically show us 3 different set of values. One which is basically the lower quartile, one is the median, and one is the upper quartile. Now, it is important for you to know some of the terminology in box plot that we usually use. Most commonly used, you probably would see Q1, Q2, and Q3, which is the lower quartile, the median, and the upper quartile. Okay, so just something for you to take note of as we start progressing into making comparisons of data with the use of the box plot. Now, another refresher for you is the box basically show us the interquartile range, which is basically showing the spread of the data in the middle 50% of the data. Okay, if you think about this closely, if we start looking at the data in terms of the quartile, This is basically the 0 quartile, this would be the 25th percentile, this is the 50th quartile, this is the 75th quartile, and obviously this will be the 100th quartile. So if you take 75, subtract 25, that's obviously going to give you 50. Alright, and that basically tells you how the data is being spread out in the middle 50% of the data. Okay, while the range basically tells us the spread of the data throughout. Okay, so we're looking at, we have to take into consideration the smallest data as well as the largest data, and that's really what separates the range and the interquartile range. The interquartile range doesn't really consider the smallest data and the largest data, which also kind of imply that if there are any existence of outliers, which generally means that data that seems really odd, that seems too big or perhaps too small, or some anomalies that you say, that's probably going to be an outlier. But we're going to come to that later on how we could find the outliers in a box plot as well. Okay, so just make sure for now you are able to identify the difference between the interquartile range as well as the range. Now, something I do really want to speak about is when it comes to box plots, it is important to start looking at how data is being skewed. Alright, and that's one of the functions that we use for box plot, where we do comparisons between a bunch of data. Okay, but I just want to introduce some terminology first, then we'll use some examples to explain how this actually works. Firstly, let's talk about the positive skew. Now, the positive skew generally works in such a way is that when you see the median, right, just by looking at the box plot visually, you probably would have seen that the median is closer to the lower quartile as compared to the upper quartile. What this generally means is that in a real life setting, when you get a situation where you get a positive skew, it simply just means or implies that most of the data is basically concentrated. Because if you think about this, if the median is closer to the lower quartile, it means that most of the data is concentrated towards the lower values. Okay, but what does it cause that positive skew? Now, again, if I were to draw a separate diagram, if I were to put the data onto a graph, it's probably going to look something like this. You're going to get a bunch of data, and it's going to be skewed towards the right, and this is something what we call the right tail. Alright, which means that most of the data is probably going to go concentrated towards the lower end. Okay, and what this basically means is that when you get a case like this, there could be scenarios where there is a presence of the outliers. I'll call this the high outliers, because outliers could be either they could be very large or could be very, very small. But the issue with that is that if you have some outliers that exist in the data set, what really happens is that it really impacts the mean, because the mean is usually influenced by very, very high outliers. And in this case, when you have a situation like this, that causes the data, in terms of the distribution of the data, to be kind of skewed to the right, and this is actually what we call a positive skew, in which that's where you get to see that little right tail that I just drew. That just could perhaps mean that there could be some high outliers that's existent in the data. Okay, so but one good catch when it comes to the box plot is if you could identify the median to be closer to the lower quartile, this could imply a positive skew of the data. Okay, now, and similarly, if we look at a negative skew, obviously it just means the other way around. It means that the median is actually closer to the upper quartile than the lower quartile. Now, your guess is probably as good as mine now. If you were to draw the data distribution on the graph, it's going to look the other way around. It's going to look something like this, where the data is going to be concentrated on the high values. Then you're going to get something what we call the left tail. Okay, so data mainly concentrated on the higher side, and that's why the median is getting close to the upper quartile, which kind of makes sense. And what causes that left tail is really because of the existence of the low outliers. Okay, possible outliers on the lower end. Okay, now this also put just the fact that if you have very low outliers, the mean could be affected as well, because the mean could actually be very low just because of the fact that you have outliers, and in this particular case you could have the mean to be actually smaller than the median. But we're not going to come to that, because generally in the box plot we just kind of disregard the mean, but I thought this is a fun fact for you to know. Okay, just why there could be skewness of the data. Alright, and this is actually what we call a negative skew. If you see the median to be closer to the upper quartile, and of course in a realistic, in a hopeful world, let's put it this way, we always hope to see symmetrical distribution where the median is of the same distance to the lower and the upper quartile. Okay, and of course the data will look something like this. I mean, in a real world setting, data usually will not be symmetrical, but there will be cases where they are very close to being symmetrical in such a way. Alright, but this is something that we'll discuss further. Something if you're interested in, I'll be happy as well to make another video to talk about normal distribution, which is something that we do in the applications and interpretation course, as well as the analysis and the approaches course in the IB. Okay, all right, now coming to this. Now, so I just want to talk a little more about the interpretation of a box plot. Sometimes it's quite obvious to see some of the common things that we see in a box plot. In the box plot, of course, we could find the highest and the minimum, or the minimum values. And in this context, if we talk about weight, it's easy to see the heaviest person and the lightest person, and of course we could find like the range as well, just to see the spread of the data. The middle 50% of the data, as I mentioned as well, which is the interquartile range, does imply the spread of the data within the middle 50% of the data as well. So it does help when you only have a single set of data and you want to analyze it by using a graph. I think a box plot can be quite useful. But I think generally a box plot is more useful when you have two or more sets of data, when you need to start making comparisons, and that's where I think you get to see the beauty of the box plot. Now, so just to reiterate what I just said, let's look at some comparisons between two box plots. So what I've done earlier is to put in the values that we had from the previous examples and to make up two different box plots, and we're going to try to see if we could make any comparisons between these two box plots. Now, I think generally if you look at these box plots, it's so obvious that the lightest goal is obviously going to be lighter than the lightest boy. That's very obvious. I think that's something that you could observe. Then again, you could be looking at the heaviest boy and the heaviest girl. Alright, it's quite obvious that the heaviest boy is going to be always heavier than the heaviest girl. The boy is probably going to be like between 62-63 kilograms, while the heaviest girl is going to be about 58 to 59 kilograms. Alright, so this is one distinction we could see just by observing the box plot. Then we could also look at basically the median. This is what you really want to observe as well, and you realize that the median for the boys is generally higher than the girls. The boys would be somewhat around 41 kilograms for the median, and the girls will probably be about between 36-37 kilograms. And that simply means on the average, the boys will generally be heavier than the girls. I'm not saying that all boys will be heavier than the girls, and that's why I brought up the keyword, which is basically on average. I think that's important because some of the boys could still be lighter than the girls, but you may have more boys which could weigh on the higher side, and that's why the median just got a bit higher for the boys as well. So it's important to use the keywords to say that the boys on the average way more than the goals. I think that's generally what I'm trying to convey the message from the box plot. Unless we do have the specific data set and we're able to find the actual value, then I think that's where we can make even more in-depth analysis of the median weight of between the boys and the girls as well. Now, so I think this is, and one thing I just want to point out is if you look at the box plot, okay, now we do know that this is the 0 quartile and this will be the 75th quartile as well, and this will be the 0 and the 75th quartile as well. And think about this, if you look at the weight of the girls from 0 to 75 and the weight of this from 0 to 75 as well, it is really obvious that 3/4 of the girls will be lighter than 3/4 of the boy, okay, just because that the upper quartile, the median, the lower quartile for the girls generally is lower than the boys. So that means that we have about 75% of the girls who will obviously have lighter weights, or who are basically lighter than the boys in this case. All right, so that's something that you could also use in the box plot if you observe it when you make the comparisons. All right, this is not rocket science. This is just based on how we use the box plot to make distinct comparisons, just by making some astute observations as well. So hopefully this gives you a rough sense on how we use the box plot to make some very obvious or distinct comparisons. Okay. So again, another example here, if you're looking at the age at death for the non-smokers and the smokers, again, the first thing I probably would have observed is that the median of the non-smokers and the smokers, it's obvious that the age of death for non-smokers, right, is actually generally, on the average, all right, would be about 67, 68 years old, while the smokers age at death would generally be about 58. So obviously the smokers on average would die earlier than the non-smokers. I think that's one conclusion you could make. Then the thing about the maximum and the minimum, there isn't really much of a comparison because they are the same. What you could talk about is that maybe because the median is closer to the upper quartile, it simply means that this could be more of a negative skewed data as well. Okay, while compared to the smokers, where you probably have more of a symmetric skewed data for this. Okay. You could also mention that the 25% of the smokers would obviously live longer than 25% of the smokers here. So again, this could be another direct comparison that you could make. Again, depending on how many comparisons you're asked to make, these are some of the very obvious ones that you could be making in the exams or maybe in your test as well. Now, I just want to show you maybe one last example, but I'm not going to go into too much details about how we could calculate the 5-number summary, where you need to calculate the minimum, the maximum, the range, the median as well, because all this can be done with the GDC. Now, of course, if you need me to show you how to do this with the GDC, like how do you make a box plot, how to calculate all the necessary figures that you need to create a box plot, just let me know and I'll make another video for that as well. Okay, but I just want to show you that if I were to do all these calculations, and again I just want to show like how we can use the box plot to make the differences. Now, assuming these numbers were all gotten from the GDC, okay, and I just want to show you some very interesting facts here. Now, if you look at the median and you look at the lower quartile, you probably would have realized that the median is actually 11 data points away from 35, and it's like 9 away from the upper quartile. That's very close. Okay, that's very close to being symmetric distribution as well. Okay, now if you look at the goals, the median obviously it's 40 away from the lower quartile and 9 away from the upper quartile, which means that it's probably more of a negative skewed data because of the fact that it's closer to the upper quartile. Okay, so in this case we could generally say that for the boys, this is probably more of a symmetrical distribution. It's not totally symmetrical, but it's very close to being symmetrical. And for the girls, this would be considered as a negative skew as well. So I just want to show you, like, even with numbers, you could easily identify how the data is being skewed. Okay, so hopefully this kind of makes sense on how we could use the skewness of the data to make comparisons between a bunch of data. Even without the box plot, we could easily come out with a conclusion like this as well. Okay, I just wanted to point out again, if you have the interquartile ratio to be 20 and the girls to be 49, what this really implies is that the boys who has a smaller interquartile range for the boys, this would imply that the spread of the data for the boys in the middle 50% of the data is going to be smaller than the girls in the middle 50%, okay, of the data. Now what does this actually mean? Okay, so if your data, the spread is smaller, this really implies that there is more consistency in the data. Now, but the fun fact about this is that if you look at the range for the boys, which is basically 84, and the girls to be 80, they're quite similar, which means that the spread for both the boys and the girls generally would be quite similar if you do consider the maximum and minimum values. But if you only consider the middle 50% of the data, it's very apparent that the boys' spread of the data is more consistent, just because of the fact that the interquartile range is way smaller than the girls. So again, this is how we could analyze the data, alright, just by looking at the numbers. Okay, we can't assume that, alright, if your interquartile range is smaller, it doesn't mean that the entire data set is more consistent than the other. You need to be looking at both separately in this case. Okay, alright, and this is how it looks like again with the box plot. Again, nothing fascinating here. It's just more about being able to plot a box plot from the numbers that you got from the, or what I call this, the 5 number summary, and being able to put this onto a box plot. Okay, that would be a requirement that you need to know as well. Okay, all right, so the last thing I do want to talk about is the outliers, as promised earlier. Again, is something that you may have learned this before, but I just want to do a quick refresher, is that outliers play a big part when it comes to data analysis using the box plot. As we probably seen earlier, the outliers could have made a big difference to how the skewness of the data would look like, and it also may affect the spread of the data with the outliers as well. So when do we actually feel that our extreme data is just too extreme? So obviously there is a benchmark, there is somewhat like a formula that you will absolutely need to know in this course for both the AI and the AA course. And I just really want to reiterate, this is really what you need to know. Now, this is not going to be in your formula booklet, so please make sure you know how to do this. Now, how do we identify the outliers is that if we have any outliers or any data that is bigger than the upper quartile plus 1.5 times the interquartile range. And the same thing for the low outliers is that if you find any data which is smaller than the lower quartile minus 1.5 times the interquartile range, that's going to give you the outliers. So you must do this check whenever you are suspecting that there could be outliers. You got to run these tests. Okay, so just for we're using the previous example, we know that the interquartile range for the boys will be 20. So we take 1.5 times 20, that will give me 30. Again, if we take the scores less than the lower quartile minus 1.5 times the interquartile range, All right. Again, because we know that the interquartile range in this case will be 5, so we take 5 times, sorry, if we take 35, the interquartile range was 30 for the boys. All right, so if we take lower quartile minus 1.5 times the interquartile range, okay, that's going to give me the outliers for this. And similarly, we will do the same thing for the outliers for the higher outliers. All right, and that basically means that anything less than 5, anything more than 85, this will be considered as outliers. So the only outlier is only going to be 91, because 91 is obviously bigger than 85. But then again, it's not really unreasonable, but this will be the test that you'll be doing for the outliers. Okay, so hopefully this clarifies what you need to do, especially when it comes to detecting the outliers. I hope this gives you a nice little crash course on the box plots. And if there is anything you need me to cover, please leave me a message, drop me some comments, and I'll be happy to do more videos as part of your revision for the AI or the AA course. All right, okay, so this is it for me for now. I'll see you the next time. All right, and please, if you like this video, please hit the like button, please subscribe to my channel. All right, I'll see you again, guys. Take care.